Hi, my name is Taylor Alexky. I'm a physics teacher's assistant for Santa Rosa Junior College, and I'm also part of the Teacher Fellow program for the 2019-2020 school year. Today is going to be an instructional video on the air drag lab. The goal for today's lab is to evaluate the relationship between air drag and terminal velocity of falling coffee filters. I just want to make note that I'm going to refer to air drag a lot, and air drag is the drag force experienced by an object in air. The ultimate question we're going to answer for today's lab is air drag proportional to terminal velocity, or is air drag proportional to terminal velocity squared? Just a reminder, terminal velocity is a constant speed that a freely falling object eventually reaches when air drag balances the weight. In the diagram provided below, I show an object released from rest where weight is the only force acting on it. In time 1 and time 2, we can see that velocity is increasing, so air drag is also increasing. And at time 3, air drag has balanced the weight. The object is no longer accelerating and it's falling at a constant velocity, which is called terminal velocity. If we were doing this lab in an actual lab setting, our experimental apparatus would have Vernier Logger Pro set up to track position over time of falling coffee filters to generate position versus time graphs and velocity versus time graphs. We would drop one coffee filter, then a combination of two, all the way up to 15, and we would use the position versus time graph and velocity versus time graph to determine terminal velocity. Here's a demo of how the coffee filters will drop. The materials we would use are a meter stick to measure the drop about 2 meters in height, Vernier Logger Pro to track position versus time, a level to ensure that the experimental apparatus is leveled, coffee filters, and a gram scale to measure the mass of the coffee filter. Why use a coffee filter for this lab? Coffee filters are able to move down in a stable position because of their angled sides. They're also able to reach terminal velocity in short distances. Another thing about them which is attractive for this lab is you can stack the coffee filters and change the mass of the object, but not necessarily the drag force parameters like shape and area. Greg was kind enough to record this entire lab for us online, and I'm going to show a demo of what the preparation would look like if you were doing this in lab.
One of the important things about measuring terminal velocity with multiples of coffee filters is the shape and the profile of the filters. If the filters are too flat, they'll flutter as they float to the ground as one, and you won't be able to get very good data. If they're too tight up and don't have a very big cross section, then when you drop the 15 of them, they will not reach terminal velocity. And you can use put the coffee filters on top of the cup and shape them to make them smaller, flatten them out on the table to make them a little wider so that they drop a little more or reach terminal velocity more quickly. And I have these shaped, so I think they'll do the job. If you put them over a ruler, you want to know what the cross-sectional area of the coffee filters. If you shined a flashlight down on the top of the filters and measured the diameter of the shadow, in this today, it seems you're about 17.7. So 17.7 centimeters in diameter. And let's see what happens. I'm going to take one filter, number 1, which I've weighed and weighs 0.906 grams. And I'm going to come over, select Logger Pro, hit collect, and let the coffee filter fall.
Okay, so Greg would go on and use those generated position versus time plots and velocity versus time plots to determine terminal velocity. I'm going to show how to do that in a separate slide. I do want to draw everyone's attention to why Greg was fitting the coffee filters over a cup. So if the coffee filters are too flat, they'll fly around, making it difficult for the motion detector to track it. And if the coffee filters are too narrow, they're not going to reach terminal velocity because they will drop too quickly. So I just wanted to drive that point home on why he was fitting them over the cup. So I know you guys don't have a Logger Pro setup at home, so we are going to do this lab a separate way. We're going to use the simulations that Greg recorded for various coffee filter combinations. He recorded them for coffee filters 1 through 5, 7, 9, 11, and 15. And he recorded them into files and to different Logger Pro simulations. So you guys will have already had Logger Pro downloaded before this lab. You guys will then download the Logger Pro simulations. You will open the Logger Pro simulations while you have Logger Pro open. So to make them work, you'll open Logger Pro, press File, Open, choose a given mass combination. Then once the mass combination opens up, you can press Analyze, Replay. Start will initiate the generation of the position versus time plots and the velocity versus time plots. So after pressing Start, 2 graphs like this will generate. And we want to know how to determine terminal velocity from these plots. So the slope of the linear portion of the position versus time plot is terminal velocity. And if you fit the linear portion of the position versus time plot with the linear fit program in Logger Pro, the slope of that is the terminal velocity. So for the first sample data plot, you would record the terminal velocity for that mass combination as 0.8193 meters per second. When I was initially doing this lab, one thing that I struggled with was determining when the position versus time graph was in fact linear and actually falling with constant velocity. So initially looking at this graph, it looks like constant velocity or terminal velocity starts at around 4 seconds. Well, you can use the velocity versus time plot as reference. When looking at the velocity versus time plot, the portion with no slope indicates constant velocity. So that's the terminal velocity. If we look at 4 seconds at the velocity versus time plot, we can see that there's some fluctuation in velocity. There's no slope at around 4.5 seconds, and so we can start the fit there for the position versus time plot. This is what your Excel spreadsheet is going to look like. We are going to give you the masses of the coffee filters. This is sample data taken from a previous lab, so it will not correspond to the actual data that you guys are given. You'll have the number of filters in the first column. You'll have the mass in the second column in grams. You'll convert that into kilograms. And the reason you'll do so is because we want to calculate the air drag. And the air drag at terminal velocity is equal to the weight. So this column right here is just the corresponding weight for the coffee filters. You'll use the position versus time graph to determine the terminal velocity, and then you'll record that and also calculate terminal velocity squared. And again, how will we determine the air drag? At terminal velocity, the air drag is equal in magnitude to the weight. So the air drag is the weight. That's how we will determine the air drag force. The way we're going to analyze this data is we're going to plot the air drag against terminal velocity and terminal velocity squared. Again, I'm going to remind you that at terminal velocity, the air drag is equal in magnitude to the gravitational force experienced by the object. So the air drag is the weight. We're going to fit each plot with a linear model and then use the fit to determine the best relationship. To determine which relationship is superior, we're going to use R squared. R squared is a statistical measure of how close the data, a given data set is to a fitted regression line. R squared values range from 0 to 1, and R squared value closer to 1 indicates a good regression line. So if we did ever have an R-squared value of 1, that would mean that 100% of the data points can be explained by the line of best fit. If we look at air drag plotted against terminal velocity, we see that it yields an R-squared value of 0.986. Now, this R-squared value is pretty close to 1, so it means that it's a good fit. But when we look at air drag plotted against terminal velocity squared, we see that the R-squared value is 0.99. This value is closer to 1, which means that this is a better line of best fit. Therefore, drag force is proportional to terminal velocity squared. So the last thing we're going to do for the lab is we want to determine what the drag coefficient is of the coffee filter. So I've provided a free body diagram to the left of a coffee filter once it's reached terminal velocity. Once it's reached terminal velocity, remember that drag force balances the weight, so these two vectors are equal in magnitude but opposite in direction. So we'll start with Newton's second law. The sum of the forces is equal to mass times acceleration. Big M is going to represent the mass of the coffee filter, but at terminal velocity, acceleration is 0. So that's why the sum of the forces is equal to 0. We have weight acting in the positive direction and drag acting in the opposite direction. So weight minus drag equals 0. We can equate weight and the air drag. And then we can plug in the equations that we know. We know that weight is equal to mass times gravity. And then I'll use the equation for drag force that was introduced in the introductory video. 1/2 the drag coefficient times the density of air, in this case, times the cross-sectional area of the coffee filter times terminal velocity squared. So I can solve for terminal velocity squared on one side. And the reason I'm going to do so is because this is the equation of our regression line. Terminal velocity squared is equal to this value times the mass of the coffee filter times gravity times the weight. So our little m, our slope of the line of best fit that we decided, is equal to 2 over the drag coefficient times the density of air times the cross-sectional area of the coffee filter. And then we can rearrange those and solve for the drag coefficient. And we will provide you with the diameter of the coffee filters in the lab instructions, but Greg did measure them out to be 17.7 centimeters, and we will also provide you with the density of air. All right, thank you so much for listening.